So let's get started. Any questions about last class? So what are we trying to do today? We will be using Zwanzig's dynamic perturbation theory to answer a very simple question, which sounds simple, but it's actually quite hard. The question is as follows. If you have a complicated n-body potential, okay, what do I mean by this? Every pair of atoms is talking to, every atom is talking to every other atom, maybe three atoms are talking at the same time, there are dihedrals involved, whatever, it's a complicated n-body potential. So this is the true n-body potential. And if you write it as a sum of two potential, you write it as a sum of a reference potential, which we denote UN0, plus some other potential. Normally, we are going to think about this other potential as being a perturbation, but it doesn't have to be. The expression that we derived last time said that the partition function for the true n-body potential is going to be related to the partition function of the reference system with the following quantity. So Zn0 is the partition function of the reference system, and that will be multiplied by a particular average, which looks like e to the power minus beta un1, the amount of the perturbation exponentiated, calculated in zero. This type of average looks funky, but it's really very simple. All you need to understand here is that un1 and un0, these are just some functions of position. These are just some functions of coordinate, right? They are potential, but what they really are, it's just some function of x, and you can calculate, or r actually, that's what we're talking about. So this is just some function of r. And we know how to calculate ensemble averages when you have some function of r, right? All this will mean is that you go to dr e to the power minus beta un multiplied by whatever this function of r is, and integral dr e to the power minus beta un. So this is this integral. Over here, just to make sure that you are with me, this un in the superscript should have a number. Should this number be 0 or 1? That number depends on this thing. The ensemble in which you are doing the averaging is given by the subscript. It's ensemble 0. So this number is going to be 0. Okay. If I wrote this thing as some function of r calculated in ensemble 0, forget about that. I wrote it, the function is e to the power minus beta un1. Forget about that. It's just some function of r. Then this would be dr f of r e to the power minus beta un divided by integral dr e to the power minus beta un. Would you agree that in this case it should be un0, right? So that's all I'm saying. Fr happens to be un1. That's another story. It's just a function, right? So this is important, and that's what makes it easier, because calculating this average is easy. This un0 in the some limit could be ideal gas. Then it's trivial, right? It just disappears everywhere. So you would keep it you would keep the integral, and you would pick your un0 in such a way that this integral is easy to calculate. Okay, that's the idea. You have a question? Look,
I'm impressed.
why? It's amazing. That's why I like it. I wish I was there. I would have, if I was alive then and I came up with this equation, I would like put it on my grave. It's that type of equation. It really is. So, but the question that I'm asking, so we will be using this equation, okay? That is the, and the nice thing about this equation is exact. un1 does not have to be small. This will be true even if un1 is large. If the perturbation is large, then this equation becomes useless, right? Because if un1 is large, then e to the power minus beta un1 is a really, 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 really small number. It's not going to help us, right?
What happened to like with kinetic energy is component, then we don't consider those.
Kinetic energy is the same, it just cancels out every side. We are perturbing the system. We are perturbing the system only in the potential part, not in the kinetic part. That's always the same. You can just write here kinetic h to the power 3 and lambda to the power 3 and h to the power 3 and lambda to the power 3, and we don't care whatever it is. It just cancels out. You have a question, Sophia? Some function. In this case, it is. In this case, f of r is, I should not use red. This thing. This is a function of r. That's the point I'm trying to make. E to the power minus beta un1. Because un is a function of r, right? The potential energy depends on r. So e to the power minus beta un1 depends on r. So yeah, go ahead.
So un0 is soft and nice, like ideal gas.
You would like it to be. So when we do van der Waals gas, you will see actually how we can do it. So the question now, which I asked of all of you, is that if you have this equation where you have un is equal to un0, so let's say that the potential energy can be split in the following way. For it to be practical, un1 has to be a perturbation, okay? But forget about that for a moment. I'm just saying that the interaction of an n-body system is split into two parts, okay? Part 1, part 2. Maybe part 1 corresponds to all pair interactions and part 2 corresponds to all triple interactions, okay? Some splitting. Given this, can you write an equation for how would the Helmholtz free energy change? It's possible that we can write down the Helmholtz free energy in the following manner, right? It's an so the question I ask of you is, if this is a nice reference system, maybe you can calculate an0 in a simple manner. But just given the knowledge of how does the potential energy separate into two things, what would be the contribution to the free energy? How do we solve this problem? Is this problem even solvable? In the general setup, can we solve this problem? So what extra does A have than U? It has the entropy, is U minus TS, right? So you're almost saying that just on the basis of how U changes, you have to calculate how S changes. That's not easy. That's going to be really hard. Maybe we can do it, maybe we cannot do it, but you can see why this is a very, very hard problem, right? In order to go from U to A, you need to calculate S. That's going to be hard. So that's why we have to manipulate partition functions, because if we know partition function, then we can back calculate all things of interest, including S. So that's what we're going to show. And so the idea here is, so the sketch of what's going to follow next is we are going to write down an as an0. So the hope is, if we did pick a nice reference system, then an0 will be easy to calculate. That's the hope. So the expression that I'm going to show you is going to look something like this. It will be an0 plus something multiplied by beta, where beta is the inverse temperature, plus something multiplied by beta square. And we will stop over there. When should such an expansion make sense? When beta is high or beta is low? When beta is small, right? And when is beta small? When temperature is high, right? So we will develop an expression which is, in math, it is known as a power series in beta. It is going to be a power series in beta. And in principle, it is exact. You just need to keep plugging as many values of beta, powers of beta as you want. It will become useless. It will become useful when beta is high or at high, when beta is small or at high temperature, which becomes useful for small beta or high temperature.
Why do we need, I mean, yeah, we need the entropy, like if you're using the U minus TS form, but can't you also say this directly? Because you know.
What is direct?
I mean, that the free energy should add up that way, because you know.
Tell me, do it.
So you've
$1,000 if you do it directly.
I'm saying you've already.
$10,000.
You've already found out what ZN is.
I haven't.
No, for the you have, right? You've derived the expression.
Yeah, but
for
does
one.
that tell you? Tell me.
Okay, so you know what that expression is. Z
Yeah,
and R.
I'm not
So
giving you $10,000 just for using that, but we have to come up with something simpler.
yeah,
That's what
you
we are
can
going to
just
use.
minus
We are going to
B.
use this. We are going to use this. So you have the right idea.
And because you're working in a canonical.
Yeah, but you will see why. So what I want you to do is to come up with a power series on the basis of that equation. That's exactly what we are going to do. So what you're saying is obvious, but it will still take a few lines to do it. Okay, I should not have offered 10,000. Too late though. So that's this equation gives us hope. This equation shows us how it will happen, right? Without this equation, we could not have thought of it. So that's what we are going to use. And I want to write down the answer. The answer turns out to be really interesting. Can anyone guess what will this term be? If you had to guess.
1.
Bad guess. Okay. One moment. Let me add something else. Actually, I made a mistake. The power series that we are going to do will be slightly different. The power series will look like the following. The first term will be actually beta to the power 0 multiplied by beta to the power, second term will be beta to the power 1, third term will be beta to the power 2, and so on and so forth. Now maybe you can answer. What should this look like? It cannot be 1. Why cannot it be 1, Nathan? No. Units, man. Units will create a problem, right? If it was 1 multiplied, what is the unit of beta to the power 0? 1, no unit, right? So what do you expect the thing in the red to, what unit should it have? Energy. That's your hint. So what do you think it should be? UN0. It won't be UN0 because UN0 is fully accounted for in AN0. UN1, there you go. It will be actually UN1 calculated in the ensemble 0. Now, this thing that I wrote in red over here is a much nicer quantity than the thing I wrote in green over here. Do you see why? Because this is exponential of minus beta UN1, while this is just UN1. You have gotten rid of the exponential. That's huge. So this is the mean value of the energy. So if the perturbation is such that on an average it is 0, then in beta to the power 0, it won't matter, which is kind of beautiful result. This second term turns out to be the variance of UN1, and we will derive that. The third term turns out to be the skew of UN1, and it's this kind of beautiful power series. So we will just, I won't derive the third term, I will just stop at variance of UN1. So that's what we are going to do. Okay. So that's the idea, what we are going to try to prove. And again, this is going to be super useful because while this, so let's call this equation number 1. While equation number 1 is exact, equation number 2, if you stop at any value of beta, equation number 2 is exact only if you consider infinitely many powers of beta, right? But that you're never going to do. You're going to stop. So in equation number 2, if you're willing to stop at beta to the power 0, then it's actually really simple. Then it's telling you that AN is equal to approximately AN0 plus average value of UN1 calculated in that ensemble. This is super interesting. This is almost telling you that entropy does not matter, right? This is telling you that the change in free energy is coming only from the potential energy, right? Entropy just doesn't matter, which is interesting. So most of the times it's useful to go up to beta to the power 1. And that's what we are going to derive today, this equation. And in Tuesday's class, we will use this to derive van der Waals gas, where our reference potential will be a hard sphere. And then we will add an attractive force and see what happens. So let's try to derive this. Okay, so what's our starting point? Our starting point is equation 1, which is Swanson's equation. Zn is equal to Zn0 multiplied by exp of minus beta I think there's a paper around 1995 or 96 by Chris Jarzinski, where the title of the paper is on the problem of calculating exponentials of very small numbers or very negative numbers, something like that. The Physical Review E single author paper. So we have this equation and we want to calculate A, right? We want to calculate the free energy of the full n-body potential. Let me just call it, I could call it AN. I'm just gonna, yeah, let's call it AN. So AN, what's the connection of Helmholtz free energy? And why am I writing Z? See, I forgot the names of the partition function. We were using Z for grand canonical, right? But that's okay. It's I said that it's canonical, right? So you know my point. We should really call it Q, but that's okay. So so keep in mind, this is canonical partition function. I can draw my face with her tongue. Sumin has very good in drawing, so she's like opposite of me. I actually find a drawing I made when I was 5 years old, and I have not improved. So AN, how do we get AN from ZN? Go ahead.
It is technically fancy garbage, but
Wow.
we don't have an n factorial term for in the Z and no.
Yeah, but it will be everywhere. N has not changed. You will have n factorial here. You'll have n factorial here. Why are you worried about it?
No, not for the Zn, but only for the Zn, not for the overall. I mean, it will.
If you calculate the true partition function, that will be a product of this one multiplied by kinetic energy partition function.
Okay, yes,
Multiplied by 1 over n factorial. It just cancels out. Okay, so that's why we don't care about it. So that's why it's called partition function, right? We have ignored all that. So n factorial cancels out. It's okay to get confused about that. So okay, so how do we get A from the canonical partition function? Go ahead. Yeah, so minus KT ln Z, where again I have changed Q to Z, but you see my point. So AN is equal to minus KT ln Z. So in other words, minus beta AN is equal to ln ZN, right? If I take the ln of this thing, what's going to happen? That's going to be ln of Zn naught plus ln of exp minus beta un1 0. So let's give them a name. So what we are doing here is to say minus beta an is equal to minus beta an0 minus beta an1. Makes sense, right? So an1 is just renaming, right? It's just branding. This is minus beta an0 and this thing is minus beta an1. Okay, so what we want to focus on is calculating minus beta an1. Minus beta an0 is some reference potential, which I'm saying is we are not worried about calculating. That's the other part, right? If you pick your reference potential poorly, then that's not going to help you. So the hope is you pick your reference potential.
There should be a beta on the right hand side. It just should be an0 minus n, because you're taking the beta to the left hand side.
I have beta every side. Why are you messing with my dimensionality? This is minus beta an, this is minus beta an0, this is minus beta an1. Oh, you mean comparing this thing?
Yeah.
Oh, you see my point, right? Yeah, it's related, you know, that sounds so okay, I'll write it down explicitly. So what I'm saying here is that minus beta an1 is minus beta ln. No, it's not minus beta ln. I was correct. Why were you confusing me? minus ln of e to the power minus beta un1 in 0, because left hand side is dimensionless, so right hand side also has to be dimensional, right? So this is what we want to calculate. What is the most tempting thing to do at this point? If you read it desperate and you have 5 minutes left in your exam, what would you do? Put the ln in and marry ln with exponential and be like they disappear. And that's a bad idea, right? We cannot do that. Go ahead.
What about the signs? The left and the right. Because the blue circle.
So that's what we have to calculate. And we cannot just put ln inside the exponential. In fact, we are going to see what it matters. There is an inequality in math, which I like a lot, which is known as Jensen's inequality. And we are going to use a form of Jensen's inequality when we work at this, but let's stick with this. So we have this, and what we are going to do is to write this as, we want to expand it as a power series, okay? So the general form of a power series is given as, you go from n is equal to 1 to infinity, you have some wn coefficient divided by n factorial multiplied by minus beta to the power n. We have one mathematician in the room. Margot, is this okay for a general power series? We could have absorbed the n factorial inside wn, right? It doesn't matter. We could have said we don't want n factorial, let n factorial be inside wn. So in general, in math, a power series means just power of some coefficient, right? So we don't really have to worry about the n factorial. We could just have kept wn. But we are going to define our power series this way. So what we want to do now is to calculate the values of W1, W2, W3. If we calculate the value of W1, then we have the term that, then we have the term in an1 that depends on beta to the power 0, right? Why? Because we have a beta over here also. So let's just work with this. So, and we are going to call this, where were we? That was equation 2. This is equation 3. Let's call this as equation 4, and this one is equation 5. So just to give you a sense for equation 5, in equation 5, if sigma stopped at n equal to 1, if you considered only the first term, what would you get? You would get minus beta n1 is approximately w1 by 1 factorial multiplied by minus beta to the power n, right? Sorry, to the power 1. Or minus beta an1 is approximately w1 to the power minus beta. Or an1 is w1, right? In this case, an will become an0 plus w1. So that's the value of the perturbation if you stopped at just the first term, and we could make it more and more accurate if we went to higher terms. So what we need to do is to calculate the values of this w, w1, w2, w3, etc. So the math is a bit, it's simple, yet you have to pay attention or it can get confusing. So we have equation 5. What I'm going to do on the next page is to take exponential of both sides of equation 5, and that's how we will proceed. Okay, and you'll see why it makes sense. We want to take exponential because exponential of minus beta an1 is zn1, right? Correct? How do we get a from z? We get a from z by taking log, right? A comes from z by taking log of z. So if you look at e to the power minus a by kt, you get z, right? And Zwanzig's relation is not for a, Zwanzig's relation is for z. So we want to look at e to the power minus beta a. So we take log of both sides of equation 5. What does that give us? That gives us exp minus beta an1, and I'm kind of dangling this n for no reason because it's n everywhere. I'll keep it. Should I keep it? No, I won't keep it. So this n just shows up everywhere, right? We are not doing a grand canonical ensemble. So there is no point in me specifying n particle all the time. Just shows up all the time. Therefore, ignore this n. So I will not write this n. Okay, that's the idea. exp of minus beta a1. So this is the left hand side of equation 5, and the right hand side is going to be exp of the summation. So exp n is equal to 1 to infinity wn by n factorial minus beta to the power n. Okay. Exponential.
Okay.
Yeah, exponential. So now think, what was the relation of A with A1? A was A0 plus A1, right? This is how we defined the change in Gibbs free energy. So what does this mean? This means A1 is equal to A minus A0, right? So therefore, exp of minus beta A1 is equal to exp of minus beta A by exp of minus beta A0. What is this ratio equal to? What is, how, again, your hint is A comes from minus 1 over beta log of Z. So what is e to the power minus beta A? Z. Which Z do we have on the top? We have the actual Z that we're interested for the full system with interaction. And on the bottom, we have the Z for the reference system. So this is Z by Z naught, exp to the power minus beta A1. So this left-hand side is Z by Z naught. And what relation do we have for Z by Z naught as per Zonzig? Z by Z naught is e to the power minus beta U1 in ensemble average 0. So this is e to the power minus beta U1 calculated in 0. And earlier we had been writing n. I have just been ignoring n, but if you're careful, you should write n also. So using equation 1. And let's call this equation 6. So we have just shown that the left-hand side of equation 6 is actually, or equation 5 becomes e to the power minus beta un. I was going to ignore the n. So u1. So the exponential of the perturbation multiplied by minus beta in ensemble 0 is equal to exponential of summation n is equal to 1 to infinity wn by n factorial minus beta to the power n. And we call this as equation 7. So it still looks quite gnarly. What we are going to do now is to really dissect both these sides of the equation more and then compare terms one by one. I'll stop for just a moment. So in class, I'm going to show it to you only for W1. Okay, because the W2 is pure algebra, and you will see why it's pure algebra. There is nothing profound in it, but the same idea, you just have to repeat for W2 and you can get it. So first, let's focus on the left-hand side. So let's focus on e to the power minus beta U1 0. So far, we haven't made use of the fact that U1 is a perturbation, right? All what we have written so far, equation 7 is precise. It's exact, there is no approximation. Now we are going to use that U1 is kind of small, okay? It's not a very large number. It's a small perturbation that we are thinking about relatively. So if we do this, we can write down this exponential inside the average, okay? We can write down this exponential. What's that going to look like? That's going to look like 1 minus beta U1 plus beta U1 whole square by 2 factorial minus dot, 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 right? Again, if you want to be exact, you just have to consider infinitely many terms in the power series and you keep going on and on and on. We are going to stop. We will stop at terms proportional to beta. This is what will allow us to recover the value of W1. If you want to calculate the value of W2, you have to go up to the third term. You can't just stop at the second term. Okay, so that's the approximation we are going to make. Okay. So again, I will write down the main equation that we are comparing. So equation 7 was exp of minus beta U1 calculated in the ensemble 0 is to be compared with exp of something that doesn't have an ensemble average. You know, that's what makes this thing nice. This power series n1 to infinity Wn by n factorial minus beta to the power n. Okay. This term, we said we are going to stop at power of beta to the power 1, beta to the power 1. So what's that going to be? That's going to be approximately 1 minus beta U1 0, right? Because we stopped. We did not go to higher power of beta. Now we can do something nice. What is the value of 1 in the ensemble 0? It's a trick question. It's a type of question Nathan likes to answer. 1, right? Do you agree, Nathan?
Yes.
Good. No, it's true. So this is minus beta U1 in ensemble 0, right? So this is 1 minus beta U1 in ensemble 0. Let's call this equation 8. And now we have to look at the right-hand side and stop that one also at certain point, right? So right-hand side, which is exp of summation n is equal to 1 to infinity Wn by n factorial minus beta to the power n. If we are going to stop at the first power of beta, what's that going to look like? That's going to look like exp W1 by 1 factorial minus beta. What is that? That is exp of minus beta W1, right? That's equation 9. So what did we just get? We got, equation 8 is the left-hand side over here, right? That's equation 8. Equation 9 is the right-hand side over here, right, in blue. And these two things are equal. So what did we get? We just got that e to the power minus beta U1 in ensemble 0 is approximately e to the power minus beta 1. Why is it approximate? Because it is a high temperature limit. We stopped at beta to the power 1. We did not go to beta power 2. Why did we care about this quantity on the left-hand side? What was the connection of this quantity with Helmholtz free energy? Well, this was e to the power minus beta A1. Remember, that was the equation. I should have numbered it. Let's call this equation number 6 prime. Equation 6 prime says that exp of minus beta A1, and that is the perturbation in the Helmholtz free energy that we were trying to calculate, is equal to exp of minus beta U1 in the reference ensemble. This equation was exact. And now we introduced an approximation that in the high temperature limit, this is e to the power minus beta W1. I think I made a math mistake, sorry. I'm just going to get 1 is equal to 1. It's not a good situation. Give me a moment. No, I haven't made a mistake, but I was about to make a mistake. It's good. What I was about to do is to conclude that therefore A1 is equal to W1. No, I don't want to do that. What I want to do is to say that therefore exp of minus beta A1 is approximately, we are going to expand e to the power minus beta W1. Okay, it's an exponential. So we'll write it as this is approximately 1 minus beta W1. Let's call this equation 10. Now compare 10 with equation 8. Okay. Compare, I will go over the steps once again. So if it looks a bit confusing, it will become clear. Compare 8 to 10. The left-hand side of 8 and 10 are the same thing. E to the power minus beta A1 is the same as the ensemble average of this thing over here is the same as this thing over here, right? That's 1/6 perturbation relation. On the right-hand side, we have two equations, right? So if we compare the right-hand side of equation 8 with equation 10, what do we get? We get 1 minus beta average of U1 0 is approximately 1 minus beta W1. Therefore, we get our final relation that we wanted to show, that W1 is equal to average of the perturbation potential in the reference ensemble. That's the relation we wanted to show. And you can see why I don't want to do the algebra for W2 in SAS. It's simple, but it's messy. Where did equation 10 come from? Equation 10 came from expanding this thing. Why? So equation 10 is an approximation, which is valid in the low beta limit. Okay, so let's go over this derivation once again, because if you really followed every step what I wrote, then you're awesome. And maybe half of you or all of you are awesome, but I would have gotten totally confused. So let's go from the very beginning. Okay, all of this that we did. Let's go over it, every equation. This equation we derived last time, right? Everyone happy with this? Zn is equal to Zn0 multiplied by e to the power minus beta Un1 in ensemble 0. So what we want to do is to say that if Un is some reference potential Un0 plus some perturbation Un1, what is going to be the value of the Helmholtz free energy of the perturbed system? That's the point we are trying to show. And I wanted to expand this as a power series, and I wrote down the result that An will depend on An0 plus something multiplied by beta to the power 0 plus something multiplied by beta to the power 1. This something multiplied by beta to the power 0, you expected that this something should have the unit of energy. And the one thing that you can think of unit of energy, it clearly cannot depend on UN0 because you're talking about the perturbation. So it's going to be UN1. So the simplest thing that it can be is the ensemble average of UN1 in reference potential. What ensemble average of UN1 in reference potential sounds like a mouthful, but what does it really mean? It means what is the average value of the perturbation you would feel if you were simulating the system, if you were studying the system in the reference potential. That's what it is. And the third term actually depends on variance. We are not going to prove that over here. So if we have this and beta to the power 0 is just 1, so this becomes AN is equal to AN0 plus average value of UN1 in the reference potential. That's what we are trying to prove. In order to prove this, we went to our Zwanzig's equation. We realized that I had switched from writing Z instead of Q, but you are smart, you were not caught, you remembered. So A, Helmholtz free energy comes from log of the canonical partition function, right? So we wrote that out. We said that the true, so this over here is the true system A, the full system, true or full, whatever you want to call it, not just reference, not just perturbation, the full thing. So if AN is equal to minus KT Zn, then and N just denotes N particles. So at some point we omitted the N. So minus beta AN is equal to log Zn, right? And log Zn is log Zn naught plus log of average of that exponential as per Zwanzig's relation. So with what we want to do is to calculate this quantity over here, which is the value of the Helmholtz free energy coming from the perturbation. That is actually defined to be, this is the definition of this quantity, right? This is how we defined it. So 3 bars means definition is plus ln of average of the exponential. It was very tempting to just put the ln inside the exponential, but we cannot do that, right? It's like, yeah, you cannot do that. It's terrible. So so we want to expand this as a power series in beta. So we wrote down our power series in equation 5, which is Wn by n factorial to the power multiplied by minus beta to the power n. We are just going to stop at n is equal to 1 because already the algebra is a bit messy. Go ahead, Nathan.
How do we decide the bounds? Why is it n equals 1, not n equals 0 for an exponential function?
Huh? What?
Because whenever you Taylor expand an exponential function, right, it goes from 0 to infinity. But you have an n equals.
Well, if you didn't stop, that's the first point you can stop. Right?
Okay.
If you expand an exponential, all exponentials to a good approximations are just 1, right? That's kind of not going to help much, right? So if you want something to happen, you have to go up to x, right?
But where you're starting is what I'm asking. So you say n equals 1 is where we're starting. But why don't we start at n equals 0 where it's 1?
No, we are not starting anywhere.
For the summation.
Oh, for the summation, I see. For the summation, we are, oh, that's a good point. For the summation, we are starting n is equal to 1 because this side we had minus beta. It's a very good question. This side we had minus beta, right? So if you started with n is equal to 0, you will have a problem. Actually, you could start at n is equal to 0. What will you get? You will get that coefficient is 0, right? By the way, you can see why this is a good equation. Anyone remembers the value of e to the power 1? No, it's really nice. It's 2.7, 1828, 18284. Isn't that crazy that it repeats? So, and if you use this equation, it will be approximately 1 plus 1 or 2. It's not that bad if you think about it, right? Gets you in the right regime. So yeah, so the main point, we started with n is equal to, this is good point. We started with n is equal to 1 to reflect that we are, so if we were not looking at an1, if we are not looking at minus beta an1, if you're looking at an1, right, then the exponential would have started at n is equal to 0, right? But we removed that part. That's what happened. So good. So we start at n is equal to 1, and that's where we stop. That's the simplest thing we can do. We just consider the first term. It's like looking at e to the power x and stopping at 1 plus x. You know, that's what we're doing here. So that term, if we do that, will become minus beta an1 is approximately w1 by 1 factorial multiplied by minus beta. So an1 is equal to w1. That's why we want to calculate w1. In order, and then if you have w1, then we know that the true system's Helmholtz free energy is going to be the reference system's Helmholtz free energy plus W1. So it's all about calculating W1 now. In order to calculate W1, we took the log of both sides of equation 5. Oh, that's why Jared was confused. Sorry, Jared.
Oh, that, yeah.
EXP, sorry, EXP of both sides of equation 5. And EXP of minus beta A1 is equal to EXP of this thing. And then just one more line, we said that EXP of minus beta A1 is this thing, is actually this thing, right? That is this one's relation, that is exact. This part is exact, right? There is no approximation here. But now we approximate and we stop at the first term, right? If you stop at the first term, then we immediately get some, by immediately, I mean one more page of algebra, but I've just tried to do everything carefully, that W1 is equal to average value of U1 naught. So this is a bunch of algebra, but once again, what is more important is that you remember the spirit of what we did. Yeah, go ahead, Sophia. Page number 5. Okay.
You had us expand the left-hand side, but then I didn't see the red circle at the top, like the finger one.
Mhm.
I didn't see how that came back into the equation at the bottom. Oh, I see it now.
Yeah. So actually the answer was already here. Answer is already in equation 8. I already did the expansion. So what you're doing here is to compare. So what I did over here is I took this expansion that I wrote in the equation 8 and wrote it again. Okay, and at the same time, I took this part in blue, e to the power summation, and I said I will just look at the first part of the summation, that becomes e to the power minus beta W1, and then I expanded that one as 1 minus beta W1. So that's why I have colored it. So so if you're looking at your notes later, all of the red is coming from the left side of equation 8, and all of the blue is coming from the right side of equation 8. Okay, that's what we'll go ahead.
So going through this derivation, I'm just a bit confused with like this end result. Isn't this like two different values that we were trying to solve for throughout that we don't have like specific calculations or something to do for it?
So are you saying this relation looks useless?
Yes.
Good. I will show you how useful it is. So let me write down. So at this point, first of all, hopefully everyone is more or less on the page that we derived it. Now, why should we be making such song and dance about why it is useful? So what did we do? We said that if UN is equal to UN0 plus UN1, then AN, the Helmholtz free energy of the true system, is Helmholtz free energy of the reference system plus ensemble average of the perturbation potential energy calculated in the reference system, right? So what are the things that we know in, so this equation has, these two equations together have 6 parts, right? The top one has 3 parts, the bottom one has 3 parts, right? So let's go over everything carefully. Which of these things do we know? Do we know UN0? That's the reference potential, right? So the things that we know, I'm going to just mark with a tick mark. Do we know UN1? We defined it for construction, right? So we know UN1, that is the perturbation we introduced. So we also know UN, right? So everything about potential energy is known. Now comes the tricky part. AN1, clearly we don't know, right? So I should not write cross, I should write question mark. That's what we are trying to calculate. AN0, here you had to take a leap of faith with me. I said that our reference potential should be simple enough that we can calculate AN0, right? That is the point here. So this is, I will write meh. Depends on reference potential. If you did a terrible job of picking your reference potential, then even AN0 will become painful. You won't be able to calculate it. So what Nix existential dilemma is, why is this any better, correct? So why is this any better? That's what comes down to the point is that, and I will show you through numerical examples why it is actually do it, but I want to give you intuition before that. Mathematically, what is UN1? UN1 is a function that depends on positions, right? So what you're doing here is to imagine that this is Nick and this is Jared, and they have a very complicated interaction, some long history of friendship or something. I don't know what's going on. Some very complicated interaction. So if I really wanted to simulate Nick and Jared talking to each other, it would be a complicated business, right? I will have to be very, very careful. But this complicated interaction, howsoever complicated it is just a function of R, right? Mathematically, it's just a function of R. So what this equation is telling us is that instead of studying Nick and Jared with that complex interaction, assume Nick and Jared are ideal gas point particles. Depends on the reference system, right? If your reference was ideal gas, and then just let them bounce around. So simulating the dynamics of the reference system is going to be very easy, right? If you pick your reference system easy enough, then at any given point of time, calculate the value of R between them and plug it in your equation to get the value of U of R. So the point here is that simulating dynamics corresponding to U of R is much harder than calculating U of R. And this really boils down to our beast with which we started 684, entropy. Really simulating the dynamics of U of R and getting everything right is very complicated. You have to reach ergodic limit, you have to worry about everything, right? But if you're doing that in the reference potential, it's very easy. You still have to calculate U of R, and if your U is a super complicated mathematical potential, that's going to be very hard. But you would have had to calculate U anyway, right? In whatever you did. Now it's just that the dynamics is very easy. So this is from a simulation perspective. From an experimental perspective, I will show you why this matters, because you can use G of R. What I will show you next is that you can calculate this ensemble average by calculating the G of R for the reference potential and forget about doing G of R for the true potential. And why is that beautiful? Because if you made up some very complicated, complex, I don't know, nano quantum polymer, whatever it is, some funky thing, and you cannot use that sample in your scattering, you cannot calculate G of R because it's so messy. However, you know what is causing the mess. You know what is the U of R for that complex polymer. What this is telling you is to turn down all the complex behavior, calculate G of R for the reference system, and just use the value of the U of R. That's why it's so powerful. So this is something actually you can use in experiments. And this will become clear as I will show you in next class as to how do we calculate UN10 using G of R of a reference potential. Any questions about this? So I'm going to stop early today because there's a lot of math. And really what you need, no, not Chandler for this one. For this one, you have to read Macquarie. If you don't have it, post on Slack. Someone has PDF. I'm not officially allowed to say I have PDF, but you might find PDF on the internet. I cannot stop you from doing that. And Macquarie's chapter 14 goes over it in nice detail. So read that. And I want to give you a flavor for what's going to happen in next class. So next class, we will show that we will study a U of R. Okay, so just radial, where the reference potential is some hard sphere, and the perturbation accounts for attractive forces. And through this, I will show you how the van der Waals equation of state emerges, and that's what we are going to do next. So our reference potential is, yeah, I will just leave it at this over here. This we will do next class. After that, we have how many classes? So that's 20. Let me draw a roadmap. So that's, no, not 20th. What's the next class? 27 minus 2, 25th April, right? 25th April. 27th April is Thursday. We will start to talk about Ising model. which is a simple way of studying phase transitions in a system. So 27th April, actually, let me look at the calendar. Which is a lot of fun. And I will prove to you that how you cannot have phase transitions in a 1D system. The lowest dimension you need to have a phase transition is a 2D. So if you really have a truly 1D system and someone tells you that a phase transition is changing, you have superconductivity appearing in a 1D system, you can call bullshit on that. You can be like, nope, no, it's not gonna happen. Either your system is 2D or it's not happening. Are any of you following the superconductivity debate that's happening right now? The same Sri Lankan guy, his work has been retracted in the past. He has again claimed a high temperature superconductor. It looks like it's again fake.
Is this the one that was presented at the March meeting?
Yeah. The guy from Rochester.
How high is the temperature?
I don't know. You can read up.
270 or something.
Very high. So 27th April, then 2nd May and 4th May. And then our last class will be 9th May. On 11th, we won't have a class. So we will do Ising model, which is a model for a phase transition. We will study what is known as a mean field approach. Let me open the class website. It's a lot of fun. You will enjoy it. The math is a bit less gnarly than what we have been doing so far. So we'll do Ising model, and we will do, so actually the first thing we will do for an Ising model is an argument which I like a lot, which is known as, let me write down this spelling, Pearl's droplet argument. It's an intuitive argument to show what happens in an Ising model. So we will study that. Then we will go to a mean field approach. I will talk about concepts such as broken symmetry and correlation length. And in the very final class, I will introduce you to a very, very basic picture of what is known as the renormalization group. If you think this stuff is crap and you should not study about it, let me point out, Onsager won the Nobel Prize for this, and Ken Wilson won the Nobel Prize for this. So we are going to look at subjects for which there have been at least 2 Nobel Prizes, and there are probably more, because Ising model is full of open problems. People think if a quantum computer happens, it might help with solving the Ising model in 3D. But and Michael Fisher, who used to be possibly the most, even more famous than Chris Jarzynski, which says something. StatMech guy here, he used to study the Ising model in 3 minus epsilon dimensions as epsilon goes to 0, something of that sort. So it's a very rich topic. We will do it in 27th, 2nd, 4th, and 9th. And then on 11th May, there is no class technically, but I might or might not do an optional class where I will cover a bit more of one other topic. I might talk about how some of this connects to machine learning. I don't know. I'll see how it goes. It might or might not happen. Maybe we have all had enough of each other by that point. We'll see how it goes. Any questions? Oh, it's on the website. Midterm will be released April 27th, Thursday. Oh, don't worry about where does the midterm stuff end. It's a different type of a midterm. You won't have such issues. It will be a fun midterm, I promise. It will be between type 1 and type 2. If not, your money back. You did not give me any money. So please read Chandler chapter 14 if you have time. That will help you understand this material, and it will also help you, not Chandler, Macquarie chapter 14, and it will also help you with the van der Waals thing next class.